Ever wished you could run complex plasma simulations without getting bogged down by the computational cost of like a full kinetic model?
Oh, tell me about it.
Well, today we're diving into a paper that tackles this head-on.
Okay.
It's called Developing a Linear Fluid Plasma Model with Accurate Kinetic Bernstein Waves, a First Step.
Catchy.
It's by Huasheng Zi from ENN Science and Technology Development Co., Ltd.,
Okay.
published just this month on February 11, 2025.
Very recent.
It proposes a new fluid model that aims to bring us the best of both worlds. The accuracy of kinetic models, specifically when it comes to those tricky Bernstein waves,
Right.
but without the computational headache.
That's a really promising development, especially for fields like fusion research,
Right.
where accurate and efficient plasma simulations are absolutely crucial.
Exactly. Imagine being able to model things like electron-cyclotron resonance heating and ion-cyclotron resonance frequency, ICRF, heating in fusion reactors with much faster turnaround times. This paper has the potential to really shake things up.
For sure.
But before we get ahead of ourselves, let's break down the problem that Z is addressing.
Okay, so at the heart of it are the limitations of kinetic models.
Okay.
They're incredibly accurate at describing plasma waves.
Yeah.
But they rely on these complex integrals that can bring even a supercomputer to its knees.
Right. I remember wrestling with the standard kinetic dispersion relation, the KDR.
Yes.
Back in grad school.
Yeah.
Was this something to do with the plasma dispersion function and an infinite series of Bessel functions?
Spot on. The KDR involves the plasma dispersion function, Z, which is already an integral in itself.
Right.
And then you have this infinite series of Bessel functions, denoted as Heenan to contend with.
Yeah.
These calculations are necessary to capture the intricate dance of wave-particle interactions happening in a plasma,
Yeah.
but they come at a steep computational cost.
So essentially, Xi's goal is to create a fluid model that can replicate that kinetic complexity, particularly the behavior of Bernstein waves, but without the computational baggage.
Precisely. A fluid model is like a simplified algebraic representation of the system.
Okay.
The real challenge lies in ensuring its accuracy across the entire spectrum of wave frequencies, which is omega,
Right.
and wave vectors, which include both parallel KZ and perpendicular KX components.
So how does Z pull off this balancing act?
Well, the first hurdle is tackling that pesky plasma dispersion function Z. Z utilizes well-established PED-A approximations to simplify it.
Okay.
It's like finding a smooth curve that closely fits the complex integral, making it much easier to work with mathematically.
So it's a shortcut.
Yeah.
But one that doesn't sacrifice accuracy.
Exactly.
I like it. What about those Bessel functions?
That's where things get really interesting. Z introduces a novel approach using something called an L-pole expansion to approximate the Bessel function dNb.
L-pole expansion, huh?
Yeah.
Care to break that down for our listeners?
Yeah. So the L-pole expansion, it shines because it maintains accuracy over a wide range of values for the Larmor radius.
And for anyone just joining us, the Larmor radius essentially tells us how wide a charged particle's orbit is in a magnetic field. Pretty crucial for understanding plasma behavior.
Exactly. And in a real plasma, you have particles with a whole spectrum of energies, meeting a wide range of Larmor radii.
Of course.
This L-pole expansion makes sure the model accurately captures the behavior of all these particles.
Right.
Even the ones with large Larmor radii, which is critical for capturing those Bernstein waves.
Okay.
It also avoids mathematical singularities,
Oh, right.
which are always a headache.
For sure.
And with careful fitting,
Yeah.
G achieves impressive accuracy, less than 1% error.
Wow. Less than 1% error using a simplified model.
Yeah,
That's remarkable.
it is.
But how do we actually put this model to work?
She ingeniously transforms the entire system into a matrix form, which allows for efficient calculation of the perpendicular wave vector, kx.
Okay.
This is the key to understanding how waves propagate in the plasma.
Okay, so matrices are coming into play now.
Right.
Can you walk us through how that transformation works?
Yeah, essentially, G combines Maxwell's equations, which govern the behavior of electromagnetic fields, with the relationship between the perturbed current, denoted as EGJ, and the electric field, denoted as ECE. This results in a set of equations that can be neatly expressed in matrix form.
So we've got this elegant fluid model in matrix form, but the real test is, does it hold up against the full-blown KDR?
Absolutely. Validation is key, and Z rigorously compares the solutions from their fluid model to those obtained from the full KDR
Okay.
for both ion cyclotron waves, ICW, and electron cyclotron waves, ECW.
And the results? I'm on the edge of my seat.
The graphs in the paper show remarkable consistency between the two models, especially for the crucial solutions that we care about most. Things like Bernstein waves, fast waves, the extraordinary mode, or X mode, and the ordinary mode, or O mode, are all captured with excellent accuracy.
So this fluid model truly delivers on its promise of kinetic level accuracy, at least for the most important parts.
Yes. And while there are some minor discrepancies in less significant solutions,
Sure.
Z attributes those mainly to the limitations of the fitting process, but overall, it's a resounding success.
All right, folks, if you want the quick summary, that's it. Z's model is a potential game changer, allowing for faster and more efficient plasma simulations without sacrificing accuracy on the solutions that matter most. But for those who want the full deep dive, stick around because we're just getting started. We're going to explore the nuances of this model, its potential applications, and what it means for the future of plasma research.
And you won't want to miss it. We'll be back in a flash to explore the fascinating depths of Z's work. Stay tuned. Welcome back, everyone. Before the break, we were discussing just how well Z's new fluid model performed when compared to the full kinetic solution.
Yeah, those graphs really drove home the point. It's remarkable how accurately this simplified model can capture the complexity of those key solutions.
What's fascinating to me is how this accuracy stems from those clever approximations of the complex mathematical functions, specifically the plasma dispersion function and those Bessel functions.
It's like finding a shortcut through a dense jungle without sacrificing your destination.
Right.
You still get there, but the journey is so much smoother.
Exactly, and I think the choice to use the L-pole expansion for approximating the Bessel function deserves a special shout-out.
We talked about how it ensures accuracy across a wide range of Larmoradi.
Right.
But I'm curious, why is that such a big deal? Our listeners are already familiar with the concept of Larmoradius.
Right.
What's the added layer of significance here?
Well, in a real plasma, you're not dealing with a single Larmor radius, but a whole distribution of them.
Okay.
You have particles zipping around with different energies, meaning their orbits have different sizes.
So the model needs to handle that diversity of particle behavior. It can't just focus on a single average Larmor radius.
Precisely, and by accurately approximating the Bessel function across that entire range of Larmor radii, the L-pole expansion ensures the model captures the collective behavior of all those particles, even the ones with those wide-sweeping orbits.
Okay.
And that's crucial for accurately representing those elusive Bernstein waves.
Right, those waves that are so important for understanding heating mechanisms in fusion plasmas.
And Bernstein waves are particularly sensitive to variations in the Larmor radius, so having a model that nails the Bessel function across a wide range of those radii is essential for capturing their behavior.
This L-pole expansion really is the unsung hero of this model.
Absolutely, and we can't forget that transformation into matrix form, that step, allows Z to actually solve for the perpendicular wave vector x, which tells us how the wave propagates through the plasma.
It's not just about theoretical accuracy, it's about turning those theoretical insights into something computationally manageable.
Exactly. By shifting the system into a matrix form, Z can harness the power of linear algebra to efficiently find solutions.
Yeah.
It's a beautiful blend of mathematical ingenuity and computational practicality.
Now, Z does mention in the paper that there are some minor discrepancies between the fluid model and the full kinetic solutions, particularly for some less important solutions.
Yes, those discrepancies are largely attributed to the inherent limitations of the fitting process for the Bessel function and the fact that the infinite series involved has to be truncated at some point.
So there's always a trade-off, right? Simplifying the model for efficiency might mean giving up a little bit of accuracy in certain edge cases.
That's true, but the beauty of this approach is that the discrepancies primarily show up in solutions that aren't as physically significant. The model excels at capturing the solutions that truly matter, the ones describing those Bernstein waves, fast waves, and those different modes of propagation.
So for practical applications like studying those heating mechanisms in fusion plasmas, this model is a huge step forward.
It is. Imagine trying to simulate those complex wave-particle interactions happening in a fusion reactor using a full kinetic model. The computational resources required would be astronomical.
Not to mention the time it would take to get results.
Exactly. This fluid model offers a much-needed shortcut, allowing researchers to obtain accurate results without needing a supercomputer and years of computation time.
Let's shift gear for a moment and talk about potential applications. Z specifically mentions ray tracing studies and full-wave simulations of ICRF heating.
Okay.
Could you unpack those for our listeners?
Of course, ray tracing is a technique used to study how waves propagate through a medium. It's analogous to tracing the path of a light beam as it travels through a lens.
So in this context, we could use this fluid model to simulate how the electromagnetic waves used for heating travel through the plasma in a fusion reactor.
Precisely, and because the fluid model is so computationally efficient, it enables more detailed and extensive ray tracing studies, which can provide invaluable insights into how to optimize heating schemes for fusion reactors.
Interesting. And what about full wave simulations?
Full-wave simulations are even more comprehensive. They take into account all the intricacies of wave propagation, including reflections, diffraction, and interactions with boundaries. They're crucial for understanding the overall energy deposition in a plasma.
So it's like a more holistic view of the healing process.
Exactly. And again, the computational efficiency of this fluid model opens the door to running full-wave simulations that would have been impractical or even impossible with those computationally demanding full kinetic models.
It sounds like this has the potential to really accelerate research in fusion energy.
Absolutely. And what's particularly exciting is that Z suggests some potential refinements to the model. For instance, they propose directly fit in the Rx function a key component of the L-pole expansion for specific cases.
So fine-tuning the model even further to match the specific needs of a research project? A
Right.
customized tool for a specific job?
Exactly. This truly is groundbreaking work. It bridges the gap between the accuracy of those complex kinetic models and the efficiency of fluid models.
It's a bridge that could lead to some remarkable discoveries in plasma physics and beyond. But before we wrap up our deep dive into Z's paper, let's take a quick moment to reflect on the broader implications of this work. All right, we've spent a good chunk of time unpacking the nuts and bolts of Z's fluid model, but let's step back for a moment and consider the bigger picture. Why should our listeners, who are at the forefront of AI and tech, care about this development in plasma physics?
Well, this paper goes beyond with plasma physics. It highlights the power of clever approximation and mathematical ingenuity to solve complex problems. Z has essentially found a way to bridge the gap between the accuracy of those computationally expensive models and the efficiency of simpler ones.
And that's a challenge that resonates across countless fields, not just plasma physics.
Absolutely. Take machine learning, for instance. We're constantly dealing with these massive data sets and intricate algorithms that demand enormous computational resources.
Finding ways to simplify those models without sacrificing accuracy is the holy grail in AI and ML right now.
Exactly. And Z's work provides a blueprint for how we can approach that challenge. By carefully dissecting the core mathematical components of a model and finding innovative ways to approximate them, we can unlock significant gains in efficiency.
And those efficiency gains translate directly into faster research, quicker insights, and ultimately accelerated progress in a wide range of fields. Precisely, and of course, let's not forget the implications for fusion research. This fluid model could revolutionize our understanding of heating mechanisms in fusion plasmas, potentially bringing us closer to that dream of clean, sustainable fusion energy. So a paper that initially seemed focused on a very specific niche in physics actually holds valuable lessons for the entire tech and AI community.
It's a perfect example of how specialized research can spark innovations that have a ripple effect across disciplines.
Now, before we wrap up, Z leaves us with a tantalizing question. They suggest that this model could be refined further by incorporating additional kinetic effects or by tackling even more complex plasma scenarios.
It's a challenge to the research community, an invitation to build on this foundation and push the boundaries of what's possible with plasma simulations.
So for all our listeners out there working on cutting-edge simulations, whether it's in physics, AI, machine learning, or any other field, take inspiration from Z's work.
Don't shy away from diving deep into the mathematical underpinnings of your models. Explore those creative approximations that can unlock new levels of efficiency without compromising the accuracy you need.
And who knows, maybe your breakthrough will be the next one we feature here on the Deep Dive. Thanks for joining us on this exciting journey into the world of plasma physics and the broader implications for computational modeling. Until next time, keep exploring, keep innovating, and keep diving deep.
And remember, sometimes the most elegant solutions are found in the most unexpected places.